There's a simple geometric interpretation to the magnitude of the cross product, which again is magnitude of A times magnitude of B times sine theta. If we put the vector A here and the vector B here emanating from common point, then we can complete a parallelogram whose sides are parallel to the A and B vectors. Now, to find the area of that parallelogram, and of course theta is the angle between the vectors. So now to find the area of that parallelogram, we can simply drop a perpendicular down to the B vector, and we'll consider this the base of the parallelogram. So what we're doing is actually finding altitude of the parallelogram. So what's that? Well, if we just look at this triangle, it's very clear that magnitude of A is the hypotenuse, and if we multiply that by the sine of theta, we get the length of this side. So this side has length, magnitude of A, times the sine of theta. Now, if we chop off this triangle here, and I'm going to kind of outline it in blue. So I'm going to take this triangle, chop it off, and then I'm going to paste it, I'm going to rotate it and paste it over here. So we chop this off here and paste it over here. What have we got? Well, now what we've got is a parallelogram, a rectangle, whose base is magnitude of B, and whose width or whose length is magnitude of B, width is magnitude of A times the sine of theta. So the area is length times width, or width times length, doesn't matter. I'll put it in this order. Magnitude of A sine theta, one of the dimensions of our rectangle, times the magnitude of B, and that is exactly what we define to be, or what we can see to be, the magnitude of the cross product. So that equals the magnitude of A cross B. You'll notice I've left the arrow off of the A here. It's important to keep arrows over things that are vectors. You lose track of what they mean if you don't do that. Let's say it's easy to lose track if you don't do that, and you really don't want to lose track. Okay, now I could have used a formula for the area of the parallelogram, but it's ridiculous to use a formula for the area of a parallelogram. You just reconstruct the parallelogram into a rectangle, and you get the dimensions of a rectangle of equivalent volume, and you can do that in your head very easily. And you can reinforce your understanding of the geometry of the situation. I'm real big on not using formulas to do things you can do very simply in a way that enhances your understanding. And while I talk about enhancing understanding, I didn't have the sine theta written here, so this clearly didn't match this, but it's clear that the sine theta belonged there. I just noticed that was missing. Just a quick note while I'm talking about this. We got vectors A, B, and C, and I make the parallelogram defined by A and B, and then I put A and B here as well and create a parallelogram. Then I get a figure that looks like what I'm about to draw. Okay, this is very crudely sketched. I guess I could sketch a dotted line back here, but you can kind of see that we form some kind of a box, but it's all skewed at various angles. Okay, the volume of this box turns out to be just the cross product of A with B crossed with C. The result is, or the volume of this figure is then going to be magnitude of A cross B. Now the magnitude of A cross B alone is the area of the base crossed with C. And what happens is when you cross A cross B with C, you're basically multiplying the length of C times the sine of the angle between C and the plane of A cross B, and you get this. Now that's not something that we want to even try to understand right now in detail. I'll also notice that the sign here is gone again. It should have been gone in the first place. This is not magnitude of A, magnitude of B. It's magnitude of A cross B. And I was reading it as if it was magnitude of A, magnitude of B, forgetting what I just written a minute earlier. In any case, this is magnitude of A times magnitude of B times the sine of theta, which is this, which is the same as this, which is this. And I apologize for that little bit of confusion. If you think it through yourself, it should become really clear. I've sketched this figure with a little color coding. The blue is like the front of the figure. So we have this, the top of the figure is in green, and this side, which is kind of in front, at least it's visible, is like so. And hopefully that makes the figure a little easier to see. You probably saw it already. It wasn't particularly well drawn, but there it is. And this thing is called a rectangular parallelepiped. A little better figure and a little terminology. This figure here, I've shaded what we might regard as the front in blue, shaded the top in green, and shaded this side in white. That might be a little clearer about what the picture is. I don't think it was completely clear, although I think most people would pick it up. And this is called a parallelepiped. Just simply make it out of little pipes running parallel and so forth. Again, just a brief addendum to what we have here.